Hi, my name is Paul Burnett, and I am with Seagate Technology, and today I'm going to be covering the topic of Introduction to HDD Field Accessible Reliability Metrics. My co-presenter today will be Matt Shumway, and so he'll add any additional information if needed. So right now, we talk about data on our lives. The intent of this is we provide a data structure that enables fleet management and failure prediction with visibility for open access to device metrics. The farm log provides access to metrics that captures health, drive usage, and environmental parameters. An ongoing farm log connection and monitoring enables and support failure predictions. We typically recommend monitoring the drives daily, but that is really dependent upon any individual infrastructure, your bandwidth, and how far back you want to keep monitoring data. The deeper your data trace, of course, is, the better predictability you can have. Farm is designed with ease of use in mind, and all metrics are fully accessible by all customers. One of the things that we did in this log is to try to provide fast access so it doesn't impact host I/O. Why farm? Why use farm when there are smart monitoring metrics? Farm provides a lot more parameters than smart. The host typically needs access to device workloads and internal metrics to do better analysis and to manage a device at scale. These can be monitored to build history and do analytics and gain insight into device usage and its overall health. It provides access to metrics that were only available using proprietary logs and tools. Some of these metrics were not part of the smart attribute data or any of the SCSI log pages, so many things have been added into that log that are not available anywhere else. Pulling the log will not impact IOPS throughput or induce any latencies to the host. Typically, this log is in the tens of milliseconds to pull the data, so we can minimize any host impact. It also allows maintainability, testability, and parsability of the data. So let me talk a little bit about some of the farm basics. The SATA farm log is 96 kilobytes in size, and the log structure is based upon pages similar to the ATA device statistics. So one page would have 32 512 byte block pages, so that'd be 16,384 bytes. And there's space for 6 of those, but we have 5 pages implemented within the farm log structure. The SAS farm log is about 9 kilobytes, and the log structure is based on T10 standard parameter codes. One of the reasons it's so much smaller than the SATA farm log is it has about the same amount of metrics, but since it's based upon parameter codes, it has a built-in expandability in how the SAS log pages are designed. So it does follow a similar principle in how we architected as the SATA logs, but still follows the same items with respect to security concerns on content visibility. So anything in this farm log will not expose any kind of user data whatsoever. It's all just metrics and counters and information like that. There is no user data being accessed in this log. The log includes metrics at device and at the head level. In many of the standards now, they have terminology for elements, which is basically a head. So this log has by head metrics, which actually provides better insight on HDD areas, since it's very head-centric about usually where the failure modes occur. The statistical groups are combined into single pages. We have the groups of general drive information, workload statistics, error statistics, environmental statistics, and reliability statistics. There are about 170 different metrics available in the log for SATA and about 140 for SAS. This continues to increase over time as our products develop new features and we find new metrics that can be inputted into the farm log to get better predictability. The parameters in the logs have a structure built in where you have a valid bit and a supported bit. So any parsers can go in and check these bits and say, is this field valid and is it supported? So in any case where neither are, then there's no additional processing to be done. So it has a built-in mechanism to say we have valid information and it can be displayed by a parser. So let's talk about farm basics in general. Enhancements to farm metrics is reviewed on an ongoing basis to improve drive health detection and usage for failure prediction. So we continually go through in every product generation, we review what metrics we have and what we feel like metrics should be added to improve predictability. And as new features are developed, some of those actually go into the farm log also, so they can be shown and reviewed. Farm uses a vendor unique saddle log that can be accessed by the read log extended command. That's using address A6. The farm for SAS, the farm log can be accessed by the log sense command, which is a T10 standard, in log page 3D, subpage 3. So let's talk about some of the farm key metrics. These are about 47 of the 140 to 170 plus metrics that we have. I'm not going to cover all these in detail, but it's just a accumulation of lists. I mean, usually in the general area, you see the power on hours, power cycle counts, how many head load events you have. Environmental information like temperature and workload. You have how many commands have been issued or random commands have been issued, along with the basic logical sectors read and written, so you can tell how much terabytes you've been transferring in the drive and calculate on the terabytes per year type of calculation. In error statistics, you have, of course, unrecoverable read errors, you have reallocated sectors, you have candidate sectors or pending locations. So those are some of the key metrics about when you start having issues, what are the things that start to show up in the drive, and those are some of the major ones that we have. The SATA has the command timeout counts. In attribute 188, we bring that in to the farm log also. And we also have like how many flash LEDs the drive had, and those are asserts, and those are typically corner case issues that the drive firmware may see, and it has to do some corrective action, so it'll assert and reset itself. And so it's usually show up as a type of command timeout kind of event. In the reliability statistics, we have the raw error rate and the seek error rate, which are attributes 1 and 7, which are available in the SATA smart attribute sector. And under the reliability statistics, we have some parameters that are tracked on the by head, and some are by head by zone, some are by head by zone with a couple of radii in there. And some that include some of our internal self-tests that can be issued to the drive that can do things like disk slip checking and BER checking. Look at some of the glist entries and pendings on the by head basis, where the other areas on a by drive basis. We have things like do we have a background refresh counts? So if drive has to go in and refresh areas as we're doing background scanning. We have MR head resistance. If you have dual readers, we'll have one for both of those. We have background scan counts. How often do you do a scan that's you have to do it or you ought to do it? And that's a priority basis about what needs to be done, or do a right fault scan, which is a more high priority. We also have some head self-tests that we do for amplitude and asymmetry, trimming bits and error, iterations to converge, and percent of code words at iteration levels. Those are self-tests we have built in on a periodic basis that we access and allow it to be seen in our metrics. We also have the fly height clearance delta, which is an angstrom value. So these are a lot of the key metrics that we use in our predictability. And sometimes we mix and match and to see, in the machine learning, which ones are the right ones to use. Not all of these will be used in any one algorithm, but as you start looking at different failure modes, some of these get more important than others in that manner. I do have a link up here that goes to a full list of metrics that we have, and that's in the back part of this presentation. I can't go into it at this point, but it is something that you can look at as you go back and look at this presentation. Risk prediction using farms. So I want to talk a little bit about how Seagate goes through and works with some of its customers. In the top graphic, you see where you have a customer which has farm logs that are pulled and records and failure records. So a customer would have those, and in the case where we work with our customers, they send that information into our enterprise Hadoop cluster, where we use that to pipeline some of that information into our machine learning modeling. From there, after we've done some analysis of the data, we do some report generation, and eventually we get to auto reports and risk assessment. So we can start generating reports on a periodic basis based upon a particular machine learning algorithm. From there, we can work with our customers to actually deploy that predictability tool at the customer site, or we can work with their quality groups to find out, would you want to do it on an exception basis or an ongoing basis in your fleet? So the big question is, can we predict potential upcoming drive failures in the customer fleet? So that really depends. I mean, yes, we can, but the question is, to what effectiveness can you do that? And so that's one of the things that always is a difficult thing to do. Predicting failures was simple. In the disk drive world, we would have done it a long time ago, but it's not. As drives develop new features and new technologies, it becomes a challenge in that area. As I mentioned earlier, the farm benefits, there's considerably more data available than the smart attributes. We have smart attributes has usually a location where you have 30 smart attributes, but the farm log has anywhere from 140 to 170 depending on the interface that's supporting the farm log. We have done engagement with several cloud customers, some with regular risk prediction reporting, that has their prediction tools operational at their sites. From there, they can go in and use this output and make decisions on whether they want to pull a drive from their fleet or continue to keep it in, and they possibly monitor it at a more frequent level. That's one thing that can be done. You can monitor it, let's say, on a weekly basis, and if it starts showing more areas where the machine learning model starts to show a worsening trend, you can actually increase the sampling to every day or every other day kind of thing. And definitely you go down to every hour if you really feel like that's necessary. Some of our methods that we use at Seagate, we store daily feeds of farm logs from our customer using some of their current and past records. We train a machine learning model using this past failure data to predict future failures based upon current log values. So we look for trends. Sometimes we do calculations based upon other values like errors based upon data transfers from the last sample. Has that error rate gotten worse, like on COBOL error rate or a G-list growth rate? Is it getting worse? And it could have a different threshold with respect to a lifetime threshold. And so we have customized packages for specific models and for customer environments. So we have seen some failure modes manifest itself in different workload environments and how the customer system interacts with the drive. From there, we send software packages to our customers to help monitor their systems, to help protect them against drive failure. And so they can go and do more proactive pulls on the data to get their drives to have a better performing fleet and getting questionable drives out of their fleet. So I want to go over an example of our machine learning results. This is one example we had where we had some customer, we fed some farm logs into the Seagate systems, and we had anywhere from 100,000 to 1 million records, and that continues to grow as we get more data. We also had some failure instances reported to Seagate, so they identified drives that had, which they identify as failures. And so from there, we train a classification model to predict future drive failures, and we target a timeline like within 7 days. That's always been a difficult thing to always say exactly how much time do you have for a drive before it starts to get into a point where it's not manageable within your fleet, within your current OS operating behavior. And if you extend that time from 7 days to 14 or 21, it can get even more difficult to have a good model to train. So you have to pick a time range where you say, this is our goal, this is what we want to get to, and try to work towards having a specific time frame which you want to train your models with. So in this particular case, how well did the model perform? Evaluating the test data, actually we showed pretty good results. In the numbers to the table to the right, you can see healthy drives and failed drives. And so we divide that into the machine learning model, how many of the healthy drives we predicted to be healthy and how many do we predict it to fail. So that would be our false trip rate. So the numbers of the 612,000 and plus 970, that would show about a 0.16% false positive rate. In the failed component area, you see we predicted 1,234 drives, which are supposed to be healthy, and they predicted to fail 694. So of those, so that which turned out 694 divided by some 1,900 drives would be around a 36% failures that are captured within the 7-day window. And that number is actually a pretty good number for predictability. I know in the early days of SMART, a lot of the rule of thumb was saying if you can get to 50% predictive capability, that would be really good. 36 is approaching that. But still there's, as you work in machine learning model and you look at more parameters and you add more information in there, what you want to do, of course, is keep reducing the false positive rate and try to continue to increase the predicted to fail rate. And that's where the challenges are. Like anything, as you start looking at the numbers, as you make a model more sensitive, if you make it too sensitive, what will start to happen is you may capture more of the failures, but you also may capture a higher rate of the predicted healthy drive. So the 0.16 false positive rate could go up to 0.3% or 0.5% or 1% or some other number. And then from there, you're actually getting a lot more drives that you have to manage, saying these drives could still run and be good in your system, but you may identify it as being a poor performing drive according to the model. So there's always a balancing act there, which you have to always manage. So here, a low false positive rate indicates a good understanding of what a good drive is. And that's always, like I said, in predictability, that's what the challenge is. Evaluating the model over a longer prediction window, a lot of times that just gives you more time to have errors occur at a wider time of drive behavior. And usually what happens there is the failure capture rate may increase, but also the false positive rate may increase. Like I said, anytime you change the sensitivity of a model, you have to manage both those parameters, the false trip rate and the capture rate. So how is the data helping some of our customers? So there's been two papers that have been, or have been issued, one by Tencent and one by Google, working about how Seagate has worked with both Tencent and the Seagate or Google with Seagate in trying to use predictability in machine learning models. I'm not going to go into these papers individually. I have a reference link in this so you can go read it for yourselves about how some of the work they've done working with Seagate to help improve their predictability and what they've done in their service center. If you look at the flow chart above, as you start working on getting any predictability machine learning model, there's a lot of infrastructure you have to have and how you manage this, of course. And then once you get information from the fleet in on your system, you have to have your diagnostic tool or your machine learning model, go through your thresholds and checks and check the farm log and decide whether you want to continue to run the drive or to fail the drive if it fails your thresholds and how you define the machine learning. So there is work that needs to be done to ensure a closed loop infrastructure to really take advantage of any kind of data analytics monitoring in the field. So I want to talk a little bit about industry standards. So should farm be an industry standard? The pro side of that is, yes, it's highly desirable to have a common tool set for customers. So if you look at one implementation, if it's across all products, that's all suppliers of disk drives and they support it, that's always really nice. The problem you get into is the con says that it limits the suppliers to provide the most up-to-date parameters. Processing and going through industry standards is very time consuming and it can change implementation, which can cause additional changes. So every supplier may not define their disk drive behavior in the very same way and how some of their internal IP is done to manage the drive to keep reliability at a very, very high level over millions and millions of drives. And because of this, they may add a feature that can help improve the reliability, and that may create a new parameter that may not be one-for-one compatible with another supplier. And because of that, it gets very difficult to say what is the right thing to put into the industry standard. So if you have a product that came out that has some new parameters, and it turns out to be very good, if you have an industry standard, you can't put them in there. You have to go through the industry standard, and usually they'll take a couple of years. So by the time you really want it for the drive of interest, it's already 2 to 3 years out. And that's where we get into the issues about how can we manage this better. And so at this point, we feel like, the farm log that we've implemented is going to keep being a vendor specific. If there's things in there that could be industry standard, we could work with the industry standard to put them into like HDD device statistics, so you can put them into a SCSI log page at some time in the future. But in the case, that's going to be a separate log that's going to have an individual poll. And if you already have it in a vendor specific log, it'll be very beneficial. The other point you get into is every supplier may have a different behavior. So you may need to have a unique machine learning model for a specific supplier. And so in the case of that, it's a different code path that you have anyway. And so the code path could be different to pull the log, parse it, and do the machine learning analysis. So at this point, we're not proposing farm as an industry standard. We're going to continue to keep it vendor specific. So is there SSD support for farm? So currently, farm is not in any Seagate SSD drives. We have internal to Seagate, we have defined metrics, but we have not created a farm log at this point. The SSD is going to serve a different kind of drive, of course, being based upon flash instead of recording media, magnetic recording media. So it has not been as widely disseminated in needing this feature at this point. And also SSD response time is, of course, significantly faster than HDD, so they can pull more metrics in a shorter period of time. So I'm going to talk a little about farm tools and accessibility. We have GitHub support for a lot of tool sets in Seagate that we are allowing to be open and free source. There are 4 places where we have in the Seagate Open C-Chest tools where we have free and open source software. Some of those are actually utilities. Some of those are actually C-based APIs. In the case of the Open C-Chest log parser, it actually supports parsing of farm to different text outputs. One is JSON, one's text, one is CSV. And some of these are available through an OpenC parser, which is a C++ based API and library to support parsing of farm logs. We have some Seagate pre-built binaries, Seadragon log utilities or Seadragon log parsers, and one will pull and the other will parse. And we have open source packages like SG3 utils through bash scripting. I've included some links in here if you're interested in going to those locations and pulling any utilities. That is freely available off the Seagate websites and the GitHub websites. So at this point, that's all the questions I have. I'd like to thank you for listening to this this breakout session, and hope you've enjoyed it.